play around with some of our identities. I showed you 3 Pythagorean identities. Were you working on studying them? So you're ready for a quiz on them, right? Should be. What are the 3? Well, one of them is sine squared theta plus cosine squared theta equals 1. Then we also learned tangent squared theta plus 1 equals secant squared. And cotangent squared theta plus 1 equals cosecant squared. And I even showed you how to prove those using x, y, and r. At least we did one. I think we'll just throw in another one here. I did this, which one did I do? Did I do could somebody tell me? Tangent squared plus 1? Okay, good. I'll do a different one. Let's just prove this one. Which is another of the Pythagorean identities. Now, in a picture, we know that if this is theta over here, and that's a right angle, and if we call this x, this y, and this r, then what would be the sine of theta? Well, first of all, we know that in trig notation, doesn't this mean the same thing? Let me talk about that first, right? When you square the sine of theta, you can write that as the sine squared of theta. What is the sine of theta? From our picture, leg opposite over hypotenuse. And what is the cosine of theta? Leg adjacent over hypotenuse. And if we square this, square that, and then if we multiply the whole equation through by r squared, we would get this, which is nothing more than the Pythagorean theorem for that same triangle we've been dealing with, meaning we did it. We have arrived. We've shown that this identity will always be true if we have definable. Now, the cool thing about this one is the sine of theta is always a real number. The one I showed you the other day, the tangent of theta, sometimes is not. In fact, sometimes you get one of those UNDs, right? At certain angles. We know that the tangent of pi over 2 was UND. And the tangent of 3 pi over 2 was UND. Well, you can't take a UND and square it. So, I guess the one I proved for you the other day, comment, that particular one was true for most values of theta. This one, because there never is a time when sine or cosine are undefined, this one is always true, no matter what value of theta you pick. Okay, I'll leave the third one maybe to you. So we've done 2 of the 3 now. So, a quick little reminder of what we were doing last time. Now, let's also, there's another thing we need to do. Let's insert another page here, and let's be reminded of all the identities I've taught you. Okay. First of all, I mean, no matter how simple, and maybe I haven't, I may be adding a new one here, but I certainly have taught you what? The reciprocal identities, namely that the cosecant is the reciprocal of the sine. You already knew that. And I taught you that the secant is 1 over the cosine of theta. And I taught you that the cotangent Okay, those are sometimes just called the reciprocal identities. Those are always true, except when you got a 1 over 0, you know, like when for example, is there a cosecant of pi radians? Well, that would depend on what the sine of pi radians is. And what's the sine of pi radians? Sine shrinks down to nothing there. And so it's 0. And what's 1 over 0? It's undefined. So, I mean, we do have those special angles where we can't take special numbers we can't take reciprocals of. Then I taught you the 3 Pythagorean identities. We'll just repeat them here. Okay. And there are 2, I should put these names down. These are the reciprocal. Boy. Yeah, things aren't going real well today. So these are the reciprocal identities. These are the Pythagorean. And now I'm going to give you 2 new ones. They're called the ratio identities. Actually, you really only have to know one of these. And then the upside down version of this is kind of the cotangent is equal to the cosine over the sine. So there's new material for you today. Now, if you think about it a minute, this shouldn't surprise you, because if you pull off a right triangle, and if we put theta down in this corner again, except I should have that up. Well, I gotta think about this. Well, if this was a unit circle, wouldn't this be 1? You know, if this was right on the circle, and this, I gotta think, then this coordinate down here would be the cosine, not the sine. And this would be the sine of theta. Right? I mean, in my behavior charts, didn't I teach you to realize that the sine of theta was always that vertical coordinate? And wasn't the cosine of theta always that horizontal coordinate? Now, if I ask you to find the tangent of theta, the leg opposite, sine theta, over the leg adjacent, cosine theta. Sure, tangent equals sine over cosine. It's almost built in. Isn't it already to what I taught you? And so, no shock. And then, isn't the cotangent just the reciprocal of this one? And so, sure enough, it's the reciprocal of sine over cosine, cosine over sine. So there should be no shock there. Okay, now, that gives us what? 8 identities on this page that we can now use to prove new trigonometric identities. And we're going to spend a little time on that today. Here's an identity they're asking us to prove. You know, and I think this is supposed to say, oh no, this is not prove, but simplify. So given that expression at the top of the page in the box, simplify it as much as you can. Okay, now this is a combination of algebra skills and knowing your trig identities. So look what I did. The first thing I did is thought, well, there's a tangent squared in both parts of this, so how about if I factor it? And so I factored tangent squared times the quantity 1 minus sine squared. Now, here's where I may have lost you a little bit. In place of 1 minus sine squared, I put a cosine squared. I'm going to show you why I did that. First of all, would you agree that if I took this identity and subtracted sine squared from both sides, wouldn't I get this? Did everybody see that? If I simply subtracted sine squared from both sides of that equation on the left, wouldn't I get the one on the right? Okay, so that means 1 minus sine squared theta is exactly the same as a cosine squared theta. Hence, on this page, I substituted in place of 1 minus sine squared, I plugged in a cosine squared. Okay, so does everybody see how I got down to that line right here? And now what did I do? I used my new ratio identity. In place of tangent squared, oh, but I never taught you this, but if tangent equals sine over cosine, then doesn't tangent squared equal sine squared over cosine squared? Yeah. So in place of tangent squared, I put in sine squared over cosine squared. And look at cosine squareds cancel. And so we really have simplified this expression quite a bit. We got it down to just sine squared x. So this is kind of a unique phase of trigonometry where we're kind of at the wedding between algebra and trigonometry a little bit. They're kind of mixed together. Everybody see that one? Okay, now let me explain what I did here. The original expression is sine squared times cosecant squared equals, I'm sorry, not equals, but minus sine squared x. Since sine and cosecant are reciprocals of each other, right? Then what happens when I multiply sine squared times cosecant squared? Since they're reciprocals, shouldn't I get 1? And so you see why I substituted a 1 in that second line there? So that's just nothing more than 1 minus sine squared. Oh, there it is again. 1 minus sine squared? Or was it 1 minus cosine squared we did before? I can't remember. That's the same one. And so we can go right back to here and say, hey, 1 minus sine squared, I know what that is. That's cosine squared. And so again, we've simplified that. Okay, now here's a little bit more challenging one. We start with, and maybe I should box it off again so we're consistent. We start with the expression in the rectangle, secant fourth x minus tangent fourth x. No trig identities give me a clue here as to what to do. But algebra actually does. I look at that and I go, isn't that the difference of two squares? And now we bring out our factoring skills. How do you factor the difference of two squares? A squared plus b squared, a squared minus b squared. And so do you see where I got my two factors then? Secant squared plus tangent squared times secant squared minus tangent squared. Okay, now Why? I seem to have dropped the second factor completely. How did this, what happened to this? How did this become a 1? Well, sorry, I'm going to have to go back again. Well, let's go back to our identity page. What would happen if we subtracted tangent squared from both sides of this one? Wouldn't it become oh yeah, secant squared minus tangent squared is nothing more than 1. Secant squared minus tangent squared is nothing more than 1. And so secant squared x minus, so this is just a big fat 1. And that's why I don't have it listed up here. And so all I have is this left. What can I do to simplify that? Well, when you're really stuck and you don't seem to know what, by the way, that's the sum of two squares, isn't it? Secant squared plus tangent squared. Can we factor the sum of two squares? That was a review question from this semester. The answer is yes, but it only happened when we used the imaginaries. Do you remember that? A squared plus b squared. Well, we know how to factor a squared minus b squared. That's the a plus b, a minus b. But the a squared plus b squared is only factorable when you use i's. A plus bi, a minus bi. Complex conjugates. We don't want to get into we don't want complex numbers in this trig stuff. So I can't factor it. Okay, let's try to go back to sine cosine. Can I somehow write secant in terms of something else? Sure, secant is nothing more than a reciprocal of the cosine. So instead of thinking it as secant squared, can't I think of it as 1 over cosine squared? And tangent squared, can you think of that in terms of sine and cosine? Yeah, that new identity I gave you today. Tangent equals sine over cosine. So tangent squared then should be sine squared over cosine squared. Okay, so that's where I got that line by my pen. And now I've got an addition. I need a common denominator. Oh, I already have one. Cool. So why not bring them together? 1 plus sine squared x over cosine squared x. And that's probably as good as we're going to do. Is that simpler than what we began with? Yeah, because we're down to nice basic sine and cosine. Okay, this idea of simplifying identities gets you warmed up for proving. And I think I'm going to, instead of getting into graphs here, I'm going to throw some of those in here. And I got to find some. I think tomorrow I'm going to do the graphing, the graphing of the 6 basic trig functions, and that'll be our trig 9, which last time I taught this course I didn't have. So today I'm going to go on and I got to find some identities. Here we go. Okay, if you're wondering where I am, I'm on page 555. And I'm trying to find a good list, a good section to get started with, because we don't have all our identities yet. Okay, I'm going to start with number 12. And I'll teach you a few basics about identity proving. So we've got the cotangent cubed of t over the cosecant of t. And so an identity is an equation. the other side, cosine t multiplied by the quantity cosecant squared t minus 1. Now here's the deal on proving an identity. We have an equation. Up until now we've just been dealing with expressions and we've been simplifying them. With an identity, the idea is to get one side of the equation to show that the two sides of the equation truly are the same. And to be pure about this, you want to leave one side totally untouched. Otherwise, what happens is if you work on both sides, you have a tendency to make your wish come true. And when you make your wish come true, that you're in your zeal to get the two sides the same, and you're trying to get the two sides to look alike. You so much want them to look alike that sometimes you're unduly influenced to make an illegal move. If you force yourself only to work on one side, you've kind of removed that temptation. And if you can just work on whichever side you want and get it to look like the other side, you are done. And so one of the tricks is to try to figure out which side should I work on. And usually it's the one that's what? A little bit more, you usually want to work on the side that's a little more complicated. You want to leave the simpler one. I don't know, this side they're pretty equal, but I think I'm going to choose to work on the right side. So you got to make a decision. Try to pick what? The one that's in a little rougher form, a little bit more there. So our job, our mission, is to take that right side and work on it and do legitimate simplifying like we just have been doing, so that with this time we have an end result in mind. This is where we want to go. Okay. Maybe I will work on the left. Sorry. Well, this one's really tough because they're both about, the left one's got a denominator, the right one. I don't know, it doesn't matter. Which side would you like me to work on? The left. Okay, I'll work on the left. First of all, look for any ideas for identities. Of the identities we've got, cotangent cubed and cosecant. The only thing I can think of is maybe we should use the reciprocal identities first. Cotangent is what? Or, it's the reciprocal of the tangent. So, isn't this really the same as, first of all, see if you figure out how I got this. Now, here's the deal. Isn't the cotangent the reciprocal of the tangent? So, do you see how cotangent cubed on top became tangent cubed on the bottom? And isn't the reciprocal of the cosecant the sine? So do you see how cosecant on the bottom became sine on the top? Are you with me on that? Okay, now, I think another thing we ought to do is change tangent into its ratio identity, which is sine cubed, tangent equals sine over cosine. So then this reads, so tangent cubed is the same as sine cubed over cosine cubed. And now we got a complex fraction. If we invert and multiply, wouldn't that bring us to this point? Does that make sense? In other words, instead of dividing by sine cubed over cosine cubed, isn't that the same as multiplying by cosine cubed over sine cubed? Okay, now can we do a cancellation? Yes. This sine cancels with one of these three down here. So now I'm down to what? That's a squared now? Okay, and now I'm going to, so it's cosine cubed over sine squared. I'm going to write it this way. So I factored out a cosine. By the way, I'm starting to peak at my goal. And do you see how my goal over here on the right has a cosine multiplied by something? So do you see why I thought I'd pull a cosine out? I've got this at least in the back of my mind, so I know I want a cosine out there. Okay, cool. Now, does anybody recognize what this is? That's just, yeah, that's cotangent squared. Okay, now make a little more space here. Now, looking back on the top, but it's not cotangent squared that I want there. I want this cosecant squared minus 1. But if you look, there's a perfect identity to help us out here. I'm going to just take a time out. Let's head back to our identity page. Look right here. If you took this guy and subtracted 1 from both sides, wouldn't you have this? Does everybody see that? From here to here, if you subtract 1 from both sides, wouldn't you get this? So what can I substitute for cosecant squared minus 1? Which am I doing? The other way? I can't remember. I'm sorry. In place of cotangent squared, I'm going to plug in cosecant squared minus 1. Whoops, one more page. And now I have arrived. Even though you can't see it anymore, you see that the left side is now exactly equal to the right side. That means we have completed our proof. Yes? The new identity I gave you, remember today, cotangent equals cosine over sine?
Oh, sorry.
And so cosine squared over sine squared is cotangent. Yep. Anybody else wondering how I got from one of the steps? Now these are some of my favorite things to do because I guess I like the trig combined with the algebra. But this is called proving trig identities. Everybody get that? I know it's on a long page, so I have problems with scrolling here. I will have this posted in several forms. So let's do another one. Let's see, I did number 12, right? So let's pick out another one here. Yeah. Say that again, please. Back on this page. So on that middle line, what did I do? Okay, to get from here to here, I simply subtracted tangent squared from both sides. So it's gone over there, and all that's left is a 1. And over here, secant squared minus tangent squared. You know, I wish we'd have had more time to do this more mature, to get you guys more into these identities. But what happens is you have to get really good at being able to read these identities backwards, you know, in these backwards forms like this. And we haven't had enough chance to really warm up to these. And if we'd have had more time for trig, a full semester, we could have really gotten into that. So we're picking out another one here. Why don't we do like 22? Again, these are on page 555. 22, 1 over sine x minus 1 over cosecant x and that's supposed to equal cosecant x minus sine x. Now this is a no-brainer. The left side is obviously in a less simple form than the right side, so this one for sure I want to work on the left side. You know what I mean? It's got fractions, so it's got work to be done on it, whereas the one on the right is in a more simpler format. Usually you want to pick the one that's in less simpler format. So let's work on the left side. Okay. Well, any observations of the left side? Yes. So what you're saying is we could substitute for that first fraction just plain cosecant x. Or, in a similar vein, somebody else might have said, hey, isn't 1 over cosecant just the same as the sine? And so either of those two, very similar, that would be a good beginning point. We could begin. What's another beginning? So first of all, I really like that idea. But I want you to expand your horizons. What's another algebraic thing we could do to begin working on the left side? Everybody, what's another algebraic thing we could do to work on that left side? So in other words, get a common denominator. Yeah, and that would be, I would say those are the three approaches. It really doesn't matter which we do first. I'll start with your suggestion in the back there. Let's just, you said 1 over sine is cosecant. So she's saying, let's begin with this move. Okay, if we do that, now what do we do with the left side? We still need a common denominator, don't we? If we're going to combine those? Okay, what would the LCD be? Well, there is only one denominator now. It's cosecant, so that means I need, and we could think of it like this over here, Lauren, right? And so wouldn't I just multiply this left fraction, top and bottom, by cosecant x?
Just take the reciprocal of 1 over cosecant and you're done.
Oh, that's true. We could do that. Yeah. Actually, it's not a whole lot of trouble. We'd be almost done, but that's even better. Okay, so let's just say, so that didn't turn out to be much of a, whoops, that didn't turn out to be much of a problem, did it? Yep. Okay, all done. That one, I should have picked something a little bit harder. Yeah, I wish they had a little, maybe I got to move. No, that's it. That's their only section. Not especially thrilled with the ones they have here. All right, how about 9? Looks like this will be our last one. Number 9. The identity is sine squared alpha minus sine fourth alpha equals cosine squared alpha minus cosine fourth alpha. Wow, these two are about exactly, did I copy that right, first of all? let's see, sine squared minus sine fourth equals cosine squared minus cosine fourth. Okay. Both sides are of absolutely equal simplicity, so it actually makes no difference which side we begin on. So I'm going to just ask for suggestions. I don't care which side you want me to work on. Left? Work on the left. No, not that one. I'm just kidding. Okay, anything you can think of that I could do to simplify this algebraically? Well, or trigonometrically. What's that? Take out a sine squared? That's what I was thinking. Okay, and I believe that should be what you get. Now, we need to turn this into a cosine problem. Isn't that thing in parentheses, doesn't that thing in parentheses ring true to you? 1 minus sine squared, 1 minus sine squared. Didn't we already use that today? There it is. What's 1 minus sine squared equal to? Cosine squared. So let's make that substitution. And what can I replace for sine squared? You know, here, you got... stuff is never where I need it. Couldn't I do this? So wouldn't it be true that sine squared is equal to 1 minus cosine squared? Okay, well, isn't that perfect? Let's plug that in. Replace the sine squared here. And what happens when you multiply it out? Ta-da! We're done. Okay, that one wasn't very hard either. So at least you're beginning to see what it would be like if we could spend a lot of time on this. We can't because we have to move on to graphing. What I'd rather have you do than practice a bunch of these for this time, next time, is I'd like to just reiterate that in addition to your chart that you now know how to, well, almost, we didn't have perfect scores, but most of you are doing pretty well there. That chart you know how to develop. You also have now what? 8 identities. Well, 3 of them I know you had to have nailed, and those were the reciprocals, or you couldn't have filled out the bottom of the chart. But do you know your 3 Pythagoreans? And then add on to that your 2 ratio identities. That's what I'd rather have you work on. Tomorrow we'll do trig graphs for trig 9. And then don't forget Wednesday and Friday review. I hope to have a review sheet handed out to you tomorrow.